For unions, meanwhile, we are describing all things that happen to be in either of our two sets. So if you want to think in terms of a Venn diagram, the union would be something like the collection of both circles in their entirety. And for that matter, if you want to think a little bit more verbally, I like to think of unions as saying the word or. So if we want to define something like A union B, that looks like a cup, that would be the set of things X, such that X is in A or X is in B. It can be in either, it can be in both. It's the collection of every possibility between the pair, or further on, as we'll see later. Where, just a quick note on history, the notation that we use with these cups and caps and such comes from the Italian mathematician Peano, who is best known for his axioms on the natural numbers, which say something to the effect of 1 is a natural number, where there's some argument over that. Then every natural number n has a natural number n prime that comes after it. So like 3 is followed by 4 is followed by 5 and so on. 1 is not the successor of any natural number except for 0 if we want 0 to be a natural number. Natural numbers with the same successor are the same. So because the successor of 3 is 4 and the successor of 3 is 4, 3 is 3. And then finally, if the set X contains 1, and for every natural number n, also its successor n prime, then the natural numbers form a subset of X, to bring in that notation from our last section. But anyway, that's a jump off to the natural numbers. Let's talk about unions first with another set of examples. So for those same sets of numbers from last time, A, B, C, and D, we now want to find A union B, A union C, and A union D. So here we're saying for A union B, give me everything that is in A or everything that is in B, which means we get all the stuff from A, 1, 2, 3, and 4, as well as all the things in B, where in particular we already have 3 and 4, so then we will get 5. Then when we talk about A union C, we might think to ourselves, well, we had 1, 2, 3, and 4, and then we have 5, 6, and 7. So, wouldn't we just get 1, 2, 3, 4, 5, 6, and 7? And the answer to that question is yes, we would. The thing about a intersection is that it can, at most, not decrease the number of elements in a set. Usually intersections will make sets smaller because you're making things more focused down to the exact places that they overlap, and if they, well, don't, you have nothing, and if they do somewhat trivially, then you have cases that aren't very interesting to look at. So those tend to make things smaller, whereas unions, because they're taking all things here as well as all things there, they tend to collect bigger sets. And in this case, A union C gets everything up to 7. Meanwhile, for A union D, because D provides nothing, really A union D would just end up being 1, 2, 3, 4, or if you prefer, A. So if you ever take the union of a set with the empty set, you're not actually adding anything to it, so it just stays the same. And then if you take a set union with a subset, the empty set being an example, same sort of thing happens. You just keep the bigger set. So it's kind of the opposite of the intersection, at least in that way. It's not always precisely the opposite, especially if we're not getting into the distinction between an exclusive and an inclusive OR, but for now, that's maybe a decent way of thinking about it. Where we have a little bit more to go here, and one particular thing we can think about to build up to it is A union B. That, when we took it, we went from a set with 4 things, stuck onto it a set with 3 things, and only got a set with 5 things, which feels a little bit odd until you actually pay attention to what the elements were. And that is an important property that we're going to talk about here in terms of cardinalities with finite unions.